The recent popularity of augmented reality devices has enabled players to participate in interactive narratives in real-world environments. Assigning locations for story events is non-trivial and demanding. In this paper, we propose an optimization-based approach to automatically adapt narratives to real spaces for AR experiences. Our approach assigns compatible locations to story events, synthesizing a navigation graph to guide players through different story branches. Here is an overview of our approach. Given a story, we represent it using a tree structure. Based on the story tree and a map associated with different zone types, our optimization-based approach distributes events onto the map considering the event's location compatibility and players' walking experiences. Our main objective during the optimization is to ensure the contextual compatibility between an event and its assigned location. For example, the event talking to a car salesperson will fit a parking lot, instead of a teaching building. Other objectives are about the walking experiences, including minimizing the overall walking distance throughout the story, and balancing the walking distances between adjacent events. We illustrate the effectiveness of our cost considerations. With the location compatibility cost, events are distributed at locations with compatible zone types. With the walking distance cost, the mean walking distance decreases. With the regularization cost, walking distances between adjacent events become similar. Here is an example optimization process. Our approach employs a Markov chain Monte Carlo method to search for a navigation graph that minimizes the total cost function. We show a simulated AR walk through a synthesized navigation graph. A player starts from the assigned location of event A to the location of event B. The player then can decide to go from event B to event C, or can choose another story branch and go from event B to event D. We tested our approach in different real-world places. Our approach distributes the story events compatibly with the zone types. In the Tokyo International Forum, Event F expects to take place in a working zone and thus happens near Grand Tokyo South Tower. In the Hong Kong Convention Center, Event J expects an institution zone and happens near the Convention Center. In the Singapore Marina Bay Sands result, Event A expects an institution zone and happens near an art school. We extend our approach with an automatic zoning inference method based on an autoencoder to replace the input of fixed zoning maps. The inferred zone types include buildings, parks, and roads. Here is an example of synthesizing a navigation graph based on the inferred zones. We extend our approach with additional constraints to handle special scenarios. Designers may specify an event center around which the story events will be distributed. We show results for 3 specified event centers. Our approach can be extended to consider a landmark's visibility, which may facilitate wayfinding, and thus favors locations from which the landmark can be seen when distributing events. In this example, events are distributed considering the CN Tower's visibility from the event locations in Toronto. We tested our approach using 2 additional stories. The results demonstrate that our approach can scale up and accommodate more complex narratives. Since our work focuses on location-aware narratives adaptation, we conducted an AR user study to validate the effectiveness of the location compatibility cost, which is our core consideration. Each participant wore an AR headset to go through a navigation graph synthesized with all cost considerations, and another navigation graph synthesized with the location compatibility cost omitted. A paired t-test suggests that the participants found the story events more compatible with their locations under the condition with all costs. We also asked human designers to manually assign locations for events of the medium-scale story. The results suggest that our approach can significantly reduce the labor work. This is the end of our video. Thank you for watching.